Hi everyone, welcome to our aromatic extraction webinar. Thank you all so much for joining. We will be talking about aromatic extraction. Barry Burr and I will be your host today. Barry Burr is our refining engineer in the office. We are both chemical engineers. I focus more on the petrochemical side of things. So that is why we are tag teaming this. The aromatics complex kind of falls right in the middle of refining and the petrochemical side of things. We're excited to be here. We're excited to answer your questions and show you how ProMax can be of value to you. We're going to cover the overview of the aromatic extraction process, what it is, why it's important, and why we care about it. Then we're going to talk a little bit about why ProMax is important to us and how ProMax can help us achieve our goals. Then we'll hand it off to Barry, and Barry will go over the ProMax model. With that model, he'll go over a case study and walk through some troubleshooting. Okay, so what is aromatic extraction? So what aromatic extraction is the conversion of naphtha and pi gas into aromatics, being benzene, toluene, and xylenes. The inlet to our extraction unit, usually what we see is about 30 to 40% aromatics. Again, this is really going to depend on any units that you have upstream. This may vary from location to location, but that is what we have seen. Today, we're going to be talking solely on the extraction unit, which is this unit here in the middle. What this is going to do is it's going to use a solvent to remove our aromatic components. Those are our money-making components. So we're going to remove them from the reformate stream and then send those to benzene, toluene, and xylene columns to separate those. And what you do with those products is going to vary based on your location, but we want to make sure that we get high purity aromatics through those columns. The raffinate stream is what we want to make sure has very little aromatics in it. So this is what we usually target and really pay close attention to make sure that we are truly removing as much of the aromatics as possible. Some of the solvents used are TTEG and sulfolane. There's a couple of other out there, but those are the two predominant ones that we see. So why do we want to extract the aromatics? So the aromatics are, like I said, money-making components. The two biggest ones that we want to focus in on is benzene and paraxylene. So benzene is very important in the production of polystyrene. The other important part is paraxylene, which is used to make polyester fiber and PET resin. Again, huge product in our everyday lives. Polyester, I'm sure you've heard of it. It's a very, very important product. So the production of paraxylene, the extraction is very, very important, especially during this crisis that we're seeing. So this is a graph of the gasoline prices over the past year. And that heavy dip that we see is March 2020. That is when COVID started. And as we can see, the prices for gasoline were extremely low. Therefore, the need to produce it was not there. The margins weren't there. So there was no reason for us to make it other than that's what our refineries are for. But the refineries that have the petrochemical complexes have the capability of producing more of the benzene, toluene, and xylenes, therefore increasing the creating better margins. So that is another reason why this aromatic extraction unit is very important during this time. We want to make sure that we are able to optimize our unit and truly get as much of those aromatics out of the stream as possible so we can make more money. Along with the really great margins right now, the petrochemical markets are expected to grow significantly over the past couple of years. There's about a 3 to 5% increase in the petrochemical market. So again, another really great reason why we want to focus on this unit and try to get as much out of it as we can. So how can ProMax bring us value? Why is this important to us? Why do we want to utilize ProMax? Well, ProMax uses a proprietary thermo package that is completely different from any other software simulator. We have done our own thermo fits to this process. The two images that you can see here, the first one is sulfolane, octane, and benzene at 99 degrees Celsius. And what we're doing here is comparing the results from a research paper, so the experimental data, and comparing that to the outputs of ProMax. As you can see from the parity plot, it is nearly a 1-to-1 ratio. So the thermo in ProMax is very closely related to the experimental values for the sulfolane benzene mix as well as that sulfolane toluene mix. And that's what I'm going to talk a little bit about. We're going to hit on how I got these numbers and how ProMax was able to help us. The paper in the bottom, liquid-liquid equilibria for ternary systems, that is the research paper that I used for these calculations. So Rosmer asked what kind of thermodynamic system is used for this modeling. We are using NRTL Robinson, but there is also some additional fits in the background that we aren't seeing that better fit this thermo package to the aromatic extraction. Okay, so let's talk about how I did those parity plots. What I did was I took the information from the research paper. What they did was at 372 Kelvin, they took samples from a raffinate and the extract stream at equilibrium. And what I'm doing is I'm taking their experimental raffinate information and their experimental extract information, putting that information into ProMax, mixing the stream. Again, this stream should be at equilibrium, heating the stream up to their specified 372 Kelvin. And what we should see is if we have good thermo, we should see that the light liquid is going to represent our raffinate from the paper, and our heavy liquid is going to represent our extract. So let me show you how I did that. In this raffinate stream, the temperature and pressure are not so important on this because we are going to be heating up to a set temperature, but we are specifying that we have a molar flow of 1 pound/mole/hour. What we've done is we've taken that research information, specified that we have sulfolane, octane, and toluene at this certain mole percent. That was our raffinate information. Our extract information, again, 1 pound/mole/hour. Specified that composition. Sent that to a mixer, heated it up, and then what we should see is the formation of a light and heavy liquid. And the light liquid should match what we are going to see in the raffinate, and then the heavy liquid should match what we see in the extract. Now, there was a lot of points in that research paper, So what I've done is I've used the really great capabilities of our ProMax scenario tool. And what that does is it opens an Excel workbook that is tied to ProMax. All I did was I put in the research parameters, and this is directly connected to ProMax. So what this is doing is it's taking these values, inputting them into the raffinate stream, and putting these components into the extract stream, and then calculating their respective ProMax outputs. So this is a very, very handy tool because I was able to do each one of these runs in about 30 seconds, which was very, very nice. So once we have the compared ProMax, raffinate, and extract numbers, I threw that into a plot, plotting the results against the experimental information. As you can see, we match closely to that 1-to-1 ratio. And I did the same for the sulfolane octane toluene mixture. So really great stuff on the ProMax side. We're able to use that scenario tool to run various different cases all very quickly, again, all tied to ProMax. So we have a question asking about, is the standard NRTL and SRK-PR, or did we change any of the binary interactions? We are using NRTL Peng-Robinson. However, this is not just a standard NRTL Peng-Robinson. We have fine-tuned our thermo to better fit the aromatic extraction. So yes, we have tuned our binary interaction parameters for aromatic extraction.
Yeah, every component in that has a pair with sulfolane was modified to match the Lee paper. So those binary interaction parameters were definitely custom calculated and then implemented into the thermo package.
And Rosmer asked if the is the feed stocked of naphtha from a CCR platforming unit, and what is the concentration of benzene versus other aromatic compounds? This is just a research paper, so they took. I don't believe we have a source that says where it exactly came from.
Yeah, they were just trying to map the entire liquid or three-phase diagram or tertiary diagram. So they didn't care. They weren't concerned with what the compositions you would see in a reformate would be. They were concerned with trying to map the entire tertiary diagram to define it.
And again, this is one component at a time. So the first case was just mapping sulfolane, octane, and benzene. There was no other aromatic components. So I hope that answers your question. Rosmer also asked if we tested with Uniquac and NRTL. Yes, both packages have been tested. NRTL Peng-Robinson is better fit with our proprietary thermo in.
For the species that were not in this paper, that were not benzene and toluene, for their pairs with sulfolane, we were able to use the predictions that Unifac liquid equilibrium would calculate. So for those pairs, we use Unifac LLE estimates in assigning values to our binary interaction parameters for the NRTL package. So it's kind of complicated how we do all that. We do have predictions or estimates for all the other species besides benzene and toluene, but certainly it would be better if we had research papers like this, but we do have pretty good estimates from Unifac that's based on functional group contributions, the molecular structures and so forth.
Okay, so I'm going to go ahead and hand it over to Barry so he can discuss the ProMax model.
All right. Thank you very much, Samantha. What we're going to go through today is a particular plant's aromatics extraction model. It's a TTEG, or glycol mixture, is a solvent, and we'll first go through some simulation details about the extraction section of the unit, and then we'll proceed to the stripping portion of the unit. There are a lot of simulation tips and features in ProMax that we'll discuss for those two sections. This model also had a simulation of the water wash section and the benzene column, but we're not going to go into those in any detail. We're going to stick to the extraction and stripping in this discussion. So the purpose of the aromatics extraction unit is to take this stream that is, it's the feed stream is the reformate or some product from a reformate splitter that is got a mixture of some aromatic compounds and mostly paraffinic or naphthenic compounds in the mixture. And our objective is to use extraction and distillation to produce a raffinate that has very, very little aromatics left in it. So we're trying to get down to, 99+% aromatics recovery. And then we're also going to produce a extract, which is almost pure aromatics with very little non-aromatics remaining in it. So that's the objective of the unit. And we do that by contacting the feed at 269 degrees is where the feed enters this extractor. In this case, this extractor runs at 160 psi, and we have a lean solvent that's coming from the stripper. The solvent itself is, in this case, it's a mixture of glycols, and we can set the concentration of the glycol mixture in our makeup blowdown block. So if we have a mixture of glycols, we can specify the composition of that mixture in our circulating lean solvent. And this makeup blowdown block will bring in additional water or glycols as needed to force that composition to be correct and flow rate. So the lean solvent feeds the top of the extractor, the charge feeds somewhere in the middle, and then we also have this recycle coming back from the stripping section, which is mainly comprised of, it's about half, well, actually in this case, it's more than half aromatics, but it's got light non-aromatics in it, and their job is to basically serve as a reflux and remove any heavy non-aromatics that might be trying to get down to the bottom into this rich solvent. So the real objective here is to make sure none of the heavy non-aromatics make it into the rich solvent. These extraction columns, it's almost kind of strange, but an extraction column is almost like an upside down distillation column. So the reflux in extraction columns is typically sent to the bottom, and it's used to clean up the rich solvent and remove some materials out of the rich solvent that you don't want to be there. And in this extraction column also is producing the material that doesn't go into the solvent phase is the raffinate. And we need to find a solvent that is very strongly attracted to the aromatics, because this raffinate leaving the top of the extractor undergoes no further processing. So it's got to be very, very lean in the aromatics, which means you need a solvent that's very attracted to the aromatics. So otherwise, if you had a solvent that didn't have that capability, you'd have to do some further cleaning up and recycling of the aromatics back to the front end. But in this case, we have a solvent that's strongly attracted to the aromatics, and basically none of the aromatics make it out of the top of the column in the raffinate phase. Inside of the column, we have a setting for the flash type. So we can specify a column to be either vapor liquid equilibrium or liquid liquid equilibrium or vapor liquid liquid equilibrium. And in this case, we choose this flash type of LLE. We have 7 ideal stages for this column, and the actual unit has 70 trays of extraction trays. So it's about a 10-to-1 tray to ideal stage ratio in these extraction columns. That's what we find works pretty well. The package that we're using, the thermo package, Samantha went into pretty good detail about the sulfolane thermodynamics. We have also some pretty nice fits. The parity plots we have with TTEG are pretty good, and the package that works best for us so far is this Unifac liquid liquid equilibrium dash Ping Robinson. That's what we're using for TTEG extraction systems. So we have some published data. We'll probably do the same thing to refine it and put it into the NRTL Ping Robinson at a later date. But for now, we're, time is of the essence. We're using Unifac LLE, and it's doing a pretty good job. And I think the main advantages we would get to go into the NRTL might be some better convergence performance or speed improvements. But we already have pretty good liquid liquid extraction accuracy, in my opinion, anyway. We have in the extraction, we have some issues we're concerned with. We have the ability to calculate certain key properties. So one thing we're calculating is the aromatics recovery. And to calculate this, I need to know the percent of aromatics, or the amount of aromatics in the charge. And I also need to know the amount of aromatics in the final extract product. And the tool we use to sum those up very easily in a stream is we have an analysis called the composition subset analysis. And you can add one of these composition subset analyses like this. And when you do add it, you can give it a name. So I'm just calling it aromatics. I can choose a special subset called C5 plus aromatics, or I could manually just check the boxes of the species I want included in this composition subset. And then we can see the mass flow sum of the aromatic species here. So we see that we have, I think I was using standard volumetric flow. We have 1,483 barrels per day of aromatics in the feed. And we have, in the washed extract, we have 1,473 barrels. So it's almost the same amount. We have nearly 100% aromatics recovery. In order to calculate this number, this 99.34%, I used a user value set. We have the ability to calculate special values, user defined values. And right here is the aromatics recovery calculation. And here is the calculator. I bring in the aromatics in the feed and the aromatics in the extract. I get the ratio, and that is the aromatics recovery value. So that's how we get a lot of these numbers that you're seeing on the flow sheet. We also have some other special numbers that we're calculating about the extraction unit, the capacity of the column to handle more, or the hydraulic capacity of the column is calculated by a property in our column sizing information called the liquid load. So when you specify the diameter of a tower and tray spacing, you're able to calculate the liquid load of a liquid extraction column. And we do this a lot with liquid treaters for amine systems, removing H2S from refinery liquid hydrocarbon streams. And we know we have some guidelines for what the maximum liquid load is, but this is a different system. So there is a different maximum liquid load for this system than we would expect with an amine system. And the amines, we don't really want to exceed 15 gallons per minute per square foot. But here we don't really know what the capacity is, but we did some research and found a correlation, the Rocha correlation. And this is not something we calculate in ProMax yet, but for this system, TTEG and this aromatic stream at these conditions, we believe that about 44 gallons per minute per square foot is the hydraulic capacity for this system. And you can see that we're getting pretty close to that liquid load in this particular case. And that might be important later on when we do the case study. We have these calculations within the columns. We have specifications, and we can calculate what are called lean approaches and rich approaches for certain species. And these are good diagnostic tools to tell you whether the simulation thinks that the reason you're not getting cleaner products is because your solvent is not clean enough. And if that were the case, you would have a high value for the lean approaches. And the other limitation might be that you don't have enough solvent circulating. But if you applied more of this clean solvent, you might reduce your levels of impurities in your products. And that would be if you had a high rich approach. So in this case, this column is rich in limited. It's if we wanted to reduce the benzene and toluene contents in this column, we would need to feed more lean solvent to it, and then the benzene and toluene values here would go down. And that's something we can see with these approach calculations. I'll do some things, or I'll show you the things that I did to the column to force the lean approaches to go high and the rich approaches to go low. I'll do that later on. But those are tools we have inside of ProMax to help us diagnose a extraction system. So I think that's all I have to say about the extraction section. So Rosmer asked, what is the ratio between the primary solvent and the feed of the aromatics? And in this case, that is not something I'm calculating at this moment. I do calculate a related property on the stripping side called the hydrocarbon load and the rich solvent. But the ratio right now, we have 22,700 barrels per day of lean solvent, and we have 5,400 barrels per day of charge. So it's about a 4-to-1 ratio of solvent to charge in this particular case. Okay, when you use an equilibrium column, does the tray spacing have any significance? In this application, it might have some impact on the liquid load. I really doubt it. I think it has more significance in vapor liquid flooding calculations, but in liquid load calculations, I don't think it's going to have any bearing on that calculation. So I don't think tray spacing would do anything on a liquid distillation column sizing case. Okay, the ProMax capability to simulate hydraulics calculations. The main hydraulics parameter in liquid equilibrium is this liquid load, at least for determining whether you're approaching capacity or not. We have some other, I don't think that our liquid columns can calculate any of these other hydraulic parameters that we're able to calculate in vapor liquid systems. So in vapor liquid equilibrium columns, we do have additional calculations we do, but in liquid I don't think the correlations exist to even calculate those things. At least, we don't know about them. So for hydraulics, I would say that the liquid load is the main property we can calculate that would be of interest to you in seeing whether you're exceeding column capacity or not. All right. Okay, I'm going to proceed to the stripping section now, talk about how it is simulated and special key parameters, operating parameters that we're interested in. After in the extraction column, the lean solvent passes through the extractor, and the lean solvent picks up a lot of all the aromatic. It picks up all the aromatics, and it picks up some non-aromatic species that you don't want to have in your extract product. So if we look at our composition here, we see that there, and of course there is a large amount of, we'll look at mass fraction. There is water and glycols, and then there's a considerable amount of benzene and toluene. There's still some of these light hydrocarbons or non-aromatic hydrocarbons that we do not really want to have in our extract product. And so you see I guess the most predominant ones are these in the C6 iso or branched alkanes. That's what we mostly have as impurities. And the benzene and toluene, this is our desired product that we do have quite a bit of. So what we want to do in the stripping column is first we're going to flash out anything that will, as we drop from a high pressure from here is 185 psig, we're going to drop in pressure down to a low pressure 9 psig. The TTEG stripping systems will operate slightly above atmospheric pressure. The sulfolane systems actually operate at a pretty strong vacuum. So, there that you would need ejectors to pull the vacuum, but here we're looking at a TTEG system and it's just running at slightly above atmospheric pressure, but there's a large pressure drop. So some of the light hydrocarbons are going to flash in this primary flash and they won't even enter the column. And the purpose of the stripping column is to apply heat and stripping steam to remove all the hydrocarbons from the solvent so that you can return a lean solvent that is good for extracting. And we're going to produce two products. We're going to produce the extract, and this is a vapor side draw. So this vapor side draw is one of our products, and then the overhead vapor is going to be condensed and recycled back to the extraction tower as that reflux that I mentioned earlier. So one of the interesting things here on this column is well, first I guess I should say that the thermo package we're using in the stripping section is Unifac VLE-Ping Robinson. We'll probably get good results with Polar Ping Robinson since we've done quite a bit of work with the glycol solvents and other processes, and we've got pretty good relationships between the glycols and water and hydrocarbons and even aromatics. So, but so far we've been using Unifac VLE-Ping Robinson as a thermo package for the stripping section. In sulfolane, we actually use Polar Ping Robinson, so we don't use the Unifac. We get definitely better performance with Polar Ping Robinson on the sulfolane strippers. But in here you see that our flash type now is vapor liquid equilibrium, and we only have a reboiler as the only piece of equipment added to this column. We have a reboiler. We're adding stripping steam to help strip any impurities out of the lean solvent. The specifications for this tower, we have several things that we're calculating, but what simulates quite well is the overhead vapor rate. We're specifying it to match a specific value, and that's going to be that plus the flash gas are going to combine to become the recycle back to the extractor. And we also set the bottoms temperature. This is a very close proxy to the purity of the lean solvent, but operationally people will control to the temperature, and that's what we are specifying in this column. Now the vapor side draw is a little bit interesting. So you can, so long as you're showing a stage on a ProMax column, if you go to stages and you check this box show stage, it will indicate the stage number in the flow sheet picture, but it also provides connection points for feeds and side draws. So it's pretty easy to just connect the ProMax stream to the connection point here. But by default, the default phase for a side draw is going to be a light liquid. So it's often not very obvious where you set the phase to be a vapor. So if you go into the connections tab on our columns, you'll see the numbers of the stages, and you see this side draw that's a vapor outlet. If you right click right where that stage 6 is, you can control the phase of that side draw. So in this case, we had to go in here and change it from light liquid to vapor to specify it as being a vapor side draw. So that's a little interesting nuance about ProMax columns. So that's basically the simulation specification details. We have some calculations that are important for simulating stripping of in this unit. We have the hydrocarbon load. That's an operating parameter that I've calculated here, and it is the non-solvent parts of the rich solvent. So the reflux plus the extract divided by the rich solvent flow rates, and that is our hydrocarbon load. So that's something that a engineer on a unit like this might be interested in. We have the steam to solvent ratio. So we want to know how much. There's a ratio here that is there's a guideline on how much steam per solvent to use, and there's also the reflux to extract ratio. We want to make sure that the reflux that we send back to the tower is in the desired range relative to the amount of extract that we're producing. So we want to see what the reflux to extract ratio is and make sure that it's not out of line. And then we're also concerned with the composition of this reflux. So we want to make sure that its aromatics content is greater than 50%. And I actually show that on the extraction side. So we're showing that we have 75% aromatics in the reflux. So the more aromatics you have, the better you're going to be able to rectify basically the heavy non-aromatic impurities out of the extractor. So the objective of the stripper is mainly to make a nice pure lean solvent that's good for extracting. Any residual aromatics that are in the lean solvent, about half of the aromatics that you leave in the lean solvent, when they go into the extractor right here, about half of the aromatic molecules are going to leave with the raffinate. So that's one of the ways that you can have poor aromatics recovery, is by having too much aromatic content in your lean solvent. And the other main way that you could have poor aromatics recovery is to have poor extraction or not enough solvent contacting your feed to the column. So you may see, in fact, in this case, what's happening is in this plant, there was measurement of aromatics in the raffinate that were higher than they would like them to be. And in the base case simulation, we were predicting that the benzene and toluene amounts will be pretty low. So the mystery we had was we were wondering, well, what would be the things that might cause the poor aromatics recovery? And we thought of about 4 different things. One of them, and we've got this little case study over here where we're saying that the things that might be causing poor aromatics recovery might be poor efficiency in the extractor, or we might have a measured rate of stripping steam that's actually higher than the actual rate. So there might be error in the stripping steam flow rate, and there might be error in the stripper bottoms temperature measurement. And there might be poor efficiency in the stripper stages. So this top one is indicative of poor extraction efficiency, and these bottom 3 are really indicative of poor stripping. So we're trying to find out if we force these things to happen in the simulation, what might cause the aromatics contents in the raffinate to resemble what are measured in the plant. So in our base case simulation, we're only getting 0.05 and 0.08% benzene and toluene, but the measurements were 1.7 and 1.2. So we thought, well, let's try to force these other effects or phenomena to occur in the simulation and see what kind of impurity values they produce and see if any of these will resemble what we're seeing in the measurements. So the first thing we did was we reduced the efficiencies of the stages in the extractor. And when we reduced the extractor stage efficiencies down to about 55%, we started getting numbers of benzene and toluene contents that were pretty comparable to what we were seeing in the measurements, but they weren't really appearing in the same way. And we thought, well, let's calculate the benzene to toluene ratio and let that be sort of a marker or a signature of this mechanism that causes poor aromatics recovery. And we also did the same thing by reducing the stripping steam from 350 to 200 barrels per day. That also caused a comparable amount of aromatics impurities in the raffinate. Then we reduced the bottoms temperature by 3 degrees. And then we reduced the stage efficiencies of the stripper down to 20%. And all these things individually, of course, we didn't do all these things together, but each one of these things individually would produce aromatic impurities in the raffinate that were on the order of what we were seeing in the measurements. So if you look at the ratios of all of these, we see that the measured benzene to toluene ratio is 1.42. And of all these other mechanisms, the one that most resembled the benzene toluene ratio in ProMax was reducing the stripper efficiency. That sort of was one thing that helped make us think that maybe something was going wrong with in the stripper. And there was another thing, the measurements of the benzene and the toluene in the lean solvent, they were measuring in the lean solvent about 0.47%. And these other mechanisms we applied, either they produced no, the base case had no aromatics in the lean solvent, and the reducing the extractor efficiency also resulted in very clean solvents. So that's a clue that reducing the extractor efficiency was not the primary mechanism. Something was causing residual or benzene and toluene to be in the lean solvent. Now the situation where we were seeing the stripper efficiency being reduced, we're actually getting quite a bit more. We needed quite a bit more benzene and toluene in the lean solvent to get that level of poor aromatics recovery than they were measuring. So this might not be the only cause, but it still looked like the most probable. And another thing, I just wanted to show that the lean approach calculations were also, as a diagnostic tool, were showing that when we applied these effects to the stripping tower, that we were seeing all of a sudden we were going from very low lean approach to very high lean approach as we made this change to have a richer lean solvent. So the lean approach calculations in the extractor were picking up on this. So you could use these approach calculations as a diagnostic tool or monitoring tool to make sure that you haven't made changes to your simulation which would lead you to a poor lean approach situation. So, there's partly, it looks like the stripper efficiency, something is going wrong in the stripper to make the stage efficiencies not be as high as we normally would think they would be. So it looks like that's happening, but because it takes a lot more impurities in the lean solvent to explain all that, it makes me think there might be two things going on at the same time. It might be that the extractor itself is operating a little bit inefficiently, and that might be part of the contribution to the poor aromatics recovery. And it might be that there's inefficiency in the stripper and some inefficiency in the extractor. And, because we're operating at a liquid load that's pretty close to what the predicted maximum liquid load is, it wouldn't surprise me if some of the poor aromatics recovery was due to some poor extraction, and some of it was due to poor stripping. Now, some comments that the customer made were that they increased the rate of the rate that they were feeding solvent to their solvent regenerator, and after that happened, it helped to improve the aromatics recovery. So they made up a lot of ground on the aromatics recovery after sending some more solvent to the solvent regenerator to clean it up. So, and he mentioned that they were having foaming in the stripper as well before they increased the rate to the solvent regenerator. So it does sound like the poor efficiency in the stripper was a major contributor to the poor aromatics recovery that they were seeing. So really, that's just a description of some key aspects about these models, and then a little commentary on a study we did to try to help somebody troubleshoot a problem they were having in this unit. Let's see, I guess that's all I have for this discussion. I'm going to go and try to answer the questions now. Rosmer asked, could you and ProMax integrate with another plant of an aromatics complex? Yes, we have the ability to. We have these different flow sheets, as you can see. So you see we have an extraction unit flow sheet and a stripping and a water wash and a benzene fractionator. And we could add extra flow sheets that have different thermo packages and component lists in them. And we just, we have some simulations that have 20 different flow sheets. They're very large. So you can just keep adding flow sheets that represent different processes that have different thermodynamics and component lists, and just go on and on. So we're able to handle quite large simulations. And one thing that's coming up in our next version of ProMax, which is pretty, really exciting, is that we can have one ProMax project, which would be, say, for instance, the extraction through the benzene column. We could have a project here, and then pass the product of the benzene column to another process unit in another ProMax project. So we can control simulation across ProMax projects with some capabilities we're adding in our upcoming ProMax 6.0. So that should be really interesting to see what can be done with that. We could really extend to, we could either try to do the full aromatics complex in one ProMax project like you see here, or we could simulate separate projects and let the cross project handling capabilities manage the simulation that way. Does ProMax have the CPA package, cubic plus association? No, we don't. I mean, at least we don't call any of our other thermo packages that. We do have a special thermo package for glycol dehydration. We have this polar addition to our Ping Robinson and our SRK equations of states. And we're very, very good with glycol dehydration using the polar additions to with just glycol dehydration. We just use Ping Robinson and SRK, and they're tuned very well for that. I mean, many operating companies and engineering companies use ProMax for designing glycol dehydration. It's one of our biggest markets. So I think we're very happy with her performance in that area.
Rosmer, something I do want to know is you're asking if we can run some case studies to fix this problem. One thing we can do is we can use the implementation of the scenario tool to vary the solvent ratio of the inlet. And what that will do is you will set let's say you're currently looking at 1.8 to 2.4. You can set that ratio up and increase by 0.05 or by 0.1, whatever you think is best, and let ProMax run based off the ratios, and you can see different parameters that you deem important, such as maybe the aromatics and the raffinate, or if you're looking at some duties, whatever parameters are important to you, we can use the scenario tool to help us look at how the unit would operate using various ratios.
If you would like to operate your solvent to aromatics ratio, there's solvent to hydrocarbon or solvent to aromatics. If you want to maintain a particular ratio, you could have the solvent flow rate be set by a calculation which ties it to the hydrocarbon flow rate or the aromatics flow rate. So you could target the ratio so that you'll have exactly the solvent to hydrocarbon or aromatics ratio that you want. That's a pretty easy thing to do for having the solvent flow rate adjust so that it meets that target.
And one other thing you asked, Rosmer, was about the feed location. That is something that can be easily changed within the ProMax column. It's you can change the feed to any stage.
I've seen some other units where they have multiple feed, like 2 different feed locations, and we can have the total solvent or total reflux be split, or the feed, we can have them split, and you can control the fraction to the splitter to make as much of that flow go to one stage or the other. I hope y'all enjoyed that. I am glad to take any questions later on by email.
One thing before we sign off, I do want to encourage everyone to follow the Bryan Research and Engineering LinkedIn page. All of our training is absolutely free. You'll get access to all of our training material. So please follow us on our LinkedIn page, and we thank you all again for attending.